Hi, folks. Today we're going to learn how to solve polynomial equations in factored form. Eventually, we're going to need to know how to factor polynomials ourselves to solve equations, but in this example, we're just focusing on the solving of the equations. So all the examples we have will be pre-factored for us. What do I mean when I say factored form? I mean, instead of having the polynomial written in standard form, I have it written as a multiplication problem. And what we're going to do is we're going to solve equations that have polynomials in them. And we're going to use this multiplication problem to help us apply the zero product property. And all of this, even though it has a fancy name, it's very simple. We basically, if we have a multiplication problem that equals zero, the only way that can happen is if one of the numbers in the multiplication problem equals zero. So for this example, if a times b equals zero, then either a is zero or b is zero. There's no other way to get zero in that situation. So let's look at an example here. We have 2x times the quantity x minus 4. This is a multiplication problem. This multiplication problem is set to equal to 0. So for this to be true, either 2x equals 0 or x minus 4 equals 0. Otherwise, those two things multiplied together could not be 0. So if I go ahead and solve for x in each of these cases, I basically took each component of the multiplication problem and set it equal to 0 as a separate equation. Here, to get x by itself on one side of the equation, I divide by 2. Here, to get x all by itself on one side of the equation, I need to add 4 to both sides. So I get x equals 4 or x equals 0. Those are both possible solutions to the equation. And so what we say is that the roots are x equals 0 and x equals 4. They are both solutions to the equation. X equals 0 and x equals 4. So let's look at why this worked. We started with a polynomial equal to 0. If you don't have 0 on one side of the equation, then you need to add or subtract variables or constant as necessary to get 0 on one side of the equation and everything else on the other side. Eventually, we'll need to factor the polynomial ourselves, but today everything's going to be pre-factored for us. And then you just set each part of the multiplication problem equal to 0 and solve for x for each part of the multiplication problem. Let's look at this example here. X minus 3, the quantity, times x minus 9, the quantity, equals 0. Well, either x minus 3 equals 0 or x minus 9 equals 0. Otherwise, this could not be a true statement. How do I solve for x? In this example, I just add 3 to both sides of the equation, so I get x equals 3. Here, I add 9 to both sides of the equation so that I get x equals 9, and those are my roots. Those are the solutions to the equation. Let's do a slightly more complicated example. Here I've got 2x plus 7 times 2x minus 7. Notice this is a difference of squares pattern from last module, but we're not trying to multiply this out. We're just trying to find the roots. So I would say either 2x plus 7 equals 0 or 2x minus 7 equals 0. This is a two-step process now to get x by itself. Remember to go in reverse PEMDAS order. I'm going to subtract 7 from both sides of the equation, and I'm left with 2x equals negative 7. And then I'm going to divide both sides of the equation by 2, and I'll get x is negative 7 halves. For this other equation over here, I'm going to add 7 to both sides. So I have 2x equals positive 7. And then I'll divide both sides by 2 and get x equals positive 7 halves. And so those are my roots. X equals negative 7 halves and positive 7 halves. Now, it is possible to end up with a repeated root. And a repeated root just means when the same root appears more than one time in a polynomial. So for instance, x minus 1 squared. Well, remember that is the same as x minus 1 times x minus 1. So either x minus 1 equals 0 or x minus 1 equals 0. Of course, that's the same problem. But it becomes important later on in math to pay attention to how many times the root appears in the problem. So so when you solve x minus 1 equals 0 and you add 1 to both sides of the equation, you get x equals positive 1. It's important to know that this root of x equals 1 is repeated. Okay. And knowing how many times it's repeated. So this appears 2 times. Another example with repeated roots. Here we've got x plus 1 times x minus 3 times x plus 1. Those are all quantities. And so again, either the x plus 1 equals 0, which appears twice, or x minus 3 equals 0. Subtracting 1 from both sides gives us x equals negative 1. Adding 3 to both sides of the equation gives us x equals positive 3. I don't need the positive thing. Okay. So those are our roots, but x equals negative 1 is a repeated root here. Okay. But those are our roots. Let's look at a little bit of factoring. Factoring out the greatest common factor. So, do all terms in the polynomial share a common factor? If so, we're going to factor that out. So, we're going to do a little bit of factoring in this module, in this chapter. So, we've got 4x to the fourth plus 24x cubed. Here, in terms of the number, do 4 and 24 share a common factor? Yes, they do. They can both be divided by 4. So I'm going to take that 4 out, and I'm left with 1 plus 6. And then do x4 and x cubed share a common factor? Yes, they do. I can factor out x cubed. And what's x to the fourth divided by x cubed? That just leaves us with 1x. And x cubed divided by x cubed causes the x's to disappear entirely. They divide away. And so this here is the factored form. Of course, we don't usually write 1x, so let me just erase that 1. So this is now the factored form of this polynomial. Now that I know how to factor out the greatest common factor, I can use that skill to help me solve slightly more complicated polynomial equations. So this next equation has a polynomial equal to 0, but this time my polynomial is not written as a multiplication problem at all. I cannot use my zero product property rule unless it's a multiplication problem. So I need to turn this into a multiplication problem if I can. And as we saw in part B above, we can factor out a greatest common factor to create a multiplication problem. So I look at the 2x squared and the 8x, and with the number values, with those coefficients out front, I see that 2 and 8 share a common factor of 2, which leaves me with 1 and the 4 inside the parentheses. Now, x squared and x, do those share a common factor? Yes, they do. They are both divisible by x. X squared divided by x leaves me with just x, and x divided by x just leaves me with 1. There's no variable left. So this is kind of the factored form of this equation, or of this expression. Again, we don't usually write the number 1 there, so I'll erase it. And this expression is equal to 0. So now I've written an equivalent equation where I factored out the greatest common factor, and now I have a multiplication problem equal to 0. Now this is just like the questions we were doing on the previous page. I'm going to set each portion of the multiplication problem equal to 0. I've got 2x times the quantity x plus 4. So either 2x equals 0 or x plus 4 equals 0. If I divide both sides by 2, I see that either x is 0, or if I subtract both sides of the equation, subtract 4 from both sides of the equation, I get that x equals -4. So these are my possible roots for this equation. Let's try another example where we have to do some factoring ourselves. So in this example, we don't have a polynomial set equal to 0. I can't use my zero product property trick unless I've got 0 on one side of the equation. So to get 0 on one side of the equation, I'm going to subtract 15n from both sides, and then I'm going to have 6n squared minus 15n equals 0. So now I'm going to be able to use my zero product property as soon as I have a multiplication problem on the left-hand side. If I don't have a multiplication problem, I can't use the zero product property trick. So I'm going to use that factoring out the greatest common factor tool that we used above in part B. And do 6 and 15 share a common factor? Yes, they do. They're both divisible by 3. So I'm going to factor out of 3. That's going to leave me a 2 here and a 5 here. I'm also going to factor out an n because I've got n squared and n, both have n in them. So I'll factor out the n. N times n is where the n squared came from. But if I've got the n outside here, I don't need an n at all here on the second term of this polynomial. And so this has now been factored, and that factored form of the polynomial is still equal to 0. Now I have a factored polynomial. I've got a multiplication problem equal to 0. So now I can use my zero product property. Either 3n equals 0 or 2n minus 5 equals 0. Solving for n, I can divide both sides here by 3, and I get that n equals 0. Here I can add 5 to both sides of the equation, and I get 2n equals 5. And then I divide both sides by 2, and I get n equals 5 halves. And so those are the roots to my equation, n equals 0 and n equals 5 halves. It's important to notice here that when you are working to get your polynomial equal to 0, you add and subtract the terms until all the variables and all the constants are on one side of the equation. You do not divide. Let me show you why you don't divide. So let me do a wrong example over here. If I had 6n squared equals 15n, and I try to divide both sides of the equation by 15n, gives you 2/5 n equals 1. Notice that 15n divided by 15n does not give you 0, it gives you 1. So now to solve for n, I need to multiply both sides of the equation by 5 halves, multiply by 5 halves, so that cancels out, and I have n equals 5 halves. Now, n equals 5 halves was one of the solutions that I had before. However, the other root disappeared. I have nothing here that said that n could possibly equal 0 because I divided away one of my possible values of n. So that's why you should subtract to get 0 on one side of the equation. You shouldn't try to divide to get rid of values of n. Let's look at a real world example now. Here is an arch in the shape of a parabola, and we can model this shape using this equation. Y equals -1/9 times the quantity x plus 18 times the quantity x minus 18. X and Y are measured in inches, and the x-axis, so when Y equals 0, that's here at floor level, going from here to here. And that's what I want to do. I want to find out how wide this arch is at floor level. So I'm going to, because I want to know at floor level, I'm going to say y equals 0. So I'm going to set this equation equal to 0, just as written, x plus 18, x minus 18. And I'm going to solve it to find the positions of this point here. I'll call it point A, and this point here, which I'll call point B. And then I can find the distance between those 2 points. So if I have this multiplication problem equal to 0, one of the components has to be equal to 0. Uh, -1/9 is not equal to 0, so it must not be that component. But I can set x plus 18 equal to 0, and I can set x minus 18 equal to 0. Solving for x, I get that x equals -18, so this point over here is at -18. And solving for x in this second problem, I get that x equals +18. What's the distance as I go from -18 to +18? To calculate the distance between 2 points, you subtract their positions from each other. So I'll do, you can either do 18 minus -18, which gives you 36 inches, or you can do -18 minus 18, which gives us -36 inches. We just take the absolute value of it because we want to know the distance between it, not a displacement, or which you would do in physics or something like that. So 36 inches here. So that's how we might use roots in a real world problem. We will certainly use roots a lot more later on in the chapter, but this is an introduction if the problem is either already factored for you, or you can do simple factoring just by taking out the greatest common factor. I hope this helped.